get started. Thank you all for coming. So today we have a new faculty member speaker. Yashar Zeighami has been at the Douglas since January of this year.
Yes.
And he works at the CIC, and he'll be giving an overview of data analysis and data science as it pertains to neuroimaging. Yashar did a really great PhD with Alan Dagger at the MNI, and then continued where he worked a lot in Parkinson's and kind of looking at one of the things that we're working on in our lab quite a bit now, which is kind of tracking the spreading of degeneration as a way of confirming or disproving the hypothesis of pathogenic proteins causing disruption to networks in the disorder. And then went on and did a really cool postdoc with Alan Evans, also at the MNI. And we're lucky to have him here as a new faculty member and giving this talk today. So thanks a lot, Yashar.
The talk today is very elementary in a sense. So I'm going over data analysis, and the talk is mainly for people who are starting, but hopefully there's stuff that might help other people who have done a lot of data analysis before as well. The in neuroimaging part is in parentheses because I just talk about how it might be used, but not a lot of application in the talk. Okay. So the goal of this presentation is basically make you familiar with the approaches to data analysis, two main approaches, and what are the terminologies in each of them, and to give you some context about these different approaches and how you can use data analysis in your work and not misuse it, hopefully. I'm not a statistician, not a computer scientist. I have an engineering background. So if you ask about proof of certain things or the details, I might not be able to answer. I'm assuming the data is already cleaned. So next week, Dr. Dadar will tell you how to clean your neuroimaging data. And then after that, come back and use it in this, you can use different approaches. I'm not also talking about causality or any particular method. So what is the goal of data analysis? We are trying to use data to solve problems. And what we have is X, which is what we are measuring as features. It can be related to our output that we want to explain why, or it might not be related, in which case we will fail to model Y based on X. But the goal is to go from X to Y and try to understand the nature or just model how X relates to Y. And the type of question we ask is Y different between two groups? So we use different data points and different features to make a model and then explain why is A different from B, or that will be the way we go. We also ask, is X associated with Y? And then that is like, does brain change with aging? Does hippocampal volume relate you to your cognition, to your memory? And at the end is, does Y change as a result of treatment, which goes close to causality. So we won't talk about it a lot, but still we can use prediction models, or we can use our normal statistical models in terms of association to approach if there is a difference between the groups after treatments and before treatments. And then at the end of each analysis that you do, the question that you are trying to ask yourself is what I'm seeing real or not? So you can see something that is significant or really significant, whatever that means, and then you can go back and say, if I add something else, or if I remove one part of the X, or if I measure my Y better, do I still get the effect, and does it make sense? The two approaches to data analysis are inference and prediction. So one of them is called data modeling culture, and the other one algorithmic modeling culture, or what we call statistics and machine learning these days. And the way each of them works, the data modeling culture basically is trying to make a function that is this is a function of your predictor variables. It includes noise, what you can't measure, what is variable to your device, or maybe in this particular experiment, And then there are certain parameters that you try to fit. And what you are trying to achieve is what they call a joint probability density of X and Y. Basically, you are trying to say if X is what I have observed, what is the probability of observing any certain Y value? And you get a distribution of Y. That process is called marginalization over X. It doesn't matter much, but you just want to know that you're trying to model how X is related to Y. And then you ask the question, which part of my features are really contributing to the way Y behaves? Is it the age? Is it the sex? Is it the hippocampal volume? Is it any other function that I'm measuring, any blood measure that is related to my variable of interest? The algorithmic modeling culture, on the other hand, doesn't want necessarily to have an interpretable model. It still tries to capture a function that relates X to Y. But the endpoint for that analysis is to get certain parameters in that model and to predict Y. And in reality, it's still using a lot of parameters. So what we are modeling is almost the same, except how we approach it. Today, we call the first approach a statistical inference. And what we do is we are trying to infer based on the parameters of the model. If it's a linear model, you want to go to your beta values and see how much they are contributing to your Y. And in the second part, the second approach, you're trying to predict. So what you are trying to say is like, can I predict the age of a subject from its brain? Can I predict the cognitive function of a subject from the brain? Can I predict what was the subject looking at if I have the activity map from an fMRI experiment? While there are different approaches, they have a lot of things in common. The one thing that is mainly in common is that we don't have access to the real generative model. So both functions that we are estimating are not the real function. Because we might be measuring X values that are approximate of what is actually contributing to what. And because of that, we are hoping that we get a real generative function, but we never do in any of the two approaches. We still estimate the F based on some parameters. It can be, the parameters can be hidden to you. You use a neural network model and you train it. You make certain assumptions about some functions in those layers, but you don't necessarily tune the parameters yourself or estimate the parameters. But there are still parameters in your model. We are still assuming that the function we are estimating represents the whole population. We are not interested in the sample that we are measuring. We are interested to generalize to the population, even if we are not predicting. To fit the F function based on X and parameters and related to Y, we need a cost function in both cases. The cost function can be the number of cases that develop a certain disease versus the actual, like the predicted number versus the actual number. It can be the difference between the age that you have predicted or estimated. It can be the amount, it can even be based on your parameters, which is called regularization. So you can say, I don't want all of my features to contribute in my estimation. I want some of them to be punished and become zero, and only really good features to contribute in my estimation of Y. In both cases, you need more data is always better. It's not that if you're not doing machine learning or if you are not doing certain type of analysis, you can get away with having noisy data or not enough data. The way they talk about how much data you need might be different, but you need data. And depending on the application, you make an acceptable threshold. Here is a bit of a difference between the two approaches, because for the inference part, mostly people care about the significance level, which has been talked about, but it's not necessarily a good threshold. So you can also care about effect size. You can say how much my variable is affecting my output, my predictive variables affect my output variable. And if it's less than a certain effect size, it's the effect of X on Y is not more than 5% or whatever you define, then even if it's significant, I'm not interested. In the machine learning approach, your acceptable threshold comes from the reliability of your model. You want a certain predictive power. You want to predict the age within 3 years, or you want to know with 90% accuracy who has a certain disease, or you want to know if certain pathway is involved or not when you want to cut that pathway if you are a surgeon. Now we go to the inference first. So the question of interest is group A different from group B? And the statistical hypothesis generally that they are different. For example, we say Alzheimer patients have lower hippocampal volume, or we say older adults have lower levels of dopaminergic neurons. But what we test actually when we do a statistical analysis and a statistical inference is that what we are seeing in our data comes from the same distribution. So we always go to the null hypothesis. We say these groups are not different. And then we try to reject the null hypothesis. And what does that mean is, we will see in a minute, but it's like you are saying what I'm seeing cannot be just by chance. The same thing happens with association. If you are saying age is associated to hippocampal volume or level of dopaminergic neurons is related to severity of a symptom, your null hypothesis is that it's not related. And if you calculate, for example, the correlation is 0. This is how we approach it. And what we define as the threshold generally is a statistical significance. And what we mean is now we have an effect size. The hippocampal volume of group A is higher than group B. But the question is how much bigger it is, and based on our observation, can it be just by chance? The level of chance that we are accepting is based, it can be the p-value of 5%, it can be based on whatever definition that you use. But after you define your cutoff probability, then you can put a number and you can say a binary decision. You can say, yes, they are different based on my cutoff. And I'm rejecting the null hypothesis that these two observations are coming from one distribution. There should be two distinct distributions that are generating these two data sets. A table. So we have decisions that we are making versus the null hypothesis. And while we don't have access to the null hypothesis, we can assume that the null hypothesis was true or false. And then we look if we have rejected the null hypothesis or not. We can correctly reject the null hypothesis. So the null hypothesis was false, and we rejected it. We can correctly not reject the null hypothesis. So the data is coming from the same distribution, and we correctly said that they are coming from the same distribution. But then we can make errors. And the errors that we are making is false positive. We are saying these two groups are different while they are not different. And the other one is we are saying they are not different while they are actually different. And each of them have different consequences based on your task. So if you really care about to find every patient that might develop Alzheimer and you want to run a clinical trial, you might really want to have false positives, but have everyone that might develop Alzheimer there. Whereas if you want to give them drugs that might be not good for them, but if they really have Alzheimer, you have no other choice, you want the other to go the other. So what the other aspect of, so what we were talking here was alpha. For the false positive, we are saying how much we are willing to have false positives. But the other aspects of any test that you do is a statistical power. And what that means is you want to reject the null hypothesis, then the null hypothesis is wrong. And what it means is if I go and take 10 patients and measure something, and then I say, okay, there was no difference between this group and my control group, that might be meaningless because the probability of finding it based on 10 subjects might be almost zero. So your study has 5% chance of finding the effect anyway, and 95% of not finding it, and you didn't find it. So you cannot actually make an inference that what you have found in your experiment is meaningful. By the way, if anyone has questions or wants to, feel free to interrupt. And so the two distributions that you are seeing here, they don't occur at the same time. We don't know which one is the real distribution of the space that we are measuring through the population. It's either the blue one or the green one. And the blue one, the center is at the 0, or null can be the mean of two are the same. So if you do the difference of the mean of two distributions, it's at 0. And the green is at the real effect size. But what you are measuring is one data point on the x-axis. You don't know where it's coming from, but you have an idea that if blue was correct, what was the distribution that would produce any experiment for a given sample size. And you also know that if you have a certain effect size, if the hippocampal volume was 20% different, how the green distribution would have looked like. And when you have a sample, you can calculate what is the probability of it coming from either of the two distributions. The results that you get, depending on the test that you use, can be a t-value and f-value, and it comes with a p-value. What you need to also know is that these t-values and f-values, as our samples have a distribution, they are also random variables. So when we get a t-value, it's not an exact number that we can rely. We can just say this is a t-value to compare to all the t-values that I could have gotten. And if my t-value is around 0 based on my sample size, it has a standard deviation. And if I get a t-value of 10, then I have a lot of evidence that to reject the null hypothesis. It's very likely that if I'm not rejecting it, I am basically being here in the green distribution. And it's as you make your sample size bigger, the green distribution becomes narrower, and the chance of getting those values just by chance becomes smaller and smaller. P-value is also a random variable. And this random variable has a uniform distribution between 0 and 1 under the null hypothesis. So if your null hypothesis is true, you have a uniform distribution. And that's why we say we go with a threshold of 5%, and we are having a false positive of 5% if we do many tests. And if our tests are independent, then we are saying each of them have 5% chance of being just by chance, and we correct for that. But when your null hypothesis is not correct, then the distribution of p-values, if you do a lot of tests, if you go around and get new data sets and get more and more people, then you will see that sometimes you might not get a significant level based on your sample size, but the distribution is favoring rejecting the null hypothesis. So you get more and more likely to reject the null hypothesis as you move forward. So that is for inference. But when you're done with your inference, there are other issues that you need to consider. The first one, and the most important one, is that the absence of evidence is not evidence of absence. What it means is, if you write in your paper that there is no association between X and Y because it was not significant, what you actually mean is I couldn't find the association, not that there is no association. Based on my sample, I didn't find any association. The other way is if you do two experiments, group A shows relationship between cognition and hippocampal volume or their gray matter density, and group B doesn't. You cannot say, therefore, these two groups are different from each other. You need to compare them directly and see that they are different in their relationship and there is an interaction. Other than that, you are just comparing them with a null that is not the same null. It's like saying person A is taller than person B and person C is taller than person D. We don't know the relationship of the two groups. The next consideration is effect size and sample size and p-value. So this is a very nice graph that shows you might have significant results when you're not including your confidence interval doesn't include your null line at odds ratio of 1 or null difference at 0. But the effect size might be so small that you need thousands and thousands of subjects to just see how the significance level. And it does not mean if you go and target that variable, you can actually make a difference, meaningful difference in the long run on your predicted value. So it might be that drinking coffee affects your brain, but it might also be that targeting, giving people more and more coffee or not letting them drink coffee doesn't change it enough that you might want to do it. Whereas it might be that you're looking at a significant level that has also a good odds ratio. So if it's smoking, then you might be like, well, maybe it's good to tell them not to smoke because now I have more risk of developing certain disorders. So it's not just significance, it's also the effect size that matters. And any effect can become significant if you have enough data. The sample size is in the denominator of the p-value. So it's almost just a matter of if you have 1 million subjects, 2 million subjects. Like if you go far enough, you will get the significance. The next one is sampling bias. And to give you an example, 40% of ADNI, Alzheimer's disease, the most famous Alzheimer's disease data set, has 40% of participants that have 17 years of education, and that is not a representative population. So if there is an effect of education or mental activity or mental reserve, this data set is not going to show us. And we need a better data set that represents our population. If you're looking at the Alzheimer's disease not in white European population, again, ADNI is not your data set. If you're interested in the cerebrovascular disease, 70% of the population have comorbidity between the two disorders, but they are removed if the disease is severe, and then you cannot say, oh, there is no contribution of vascular problems in Alzheimer's or cognitive impairment because I didn't find it. Meta-analysis, if you have really nice body of literature, then you can, basically what you are trying to achieve is to put the data points on that green distribution or blue distribution from before and say, okay, now I have an estimate of the distribution. And I think what we found was not real, or it was actually real. Because now I have a distribution, I can estimate the t-values distribution. I know it contained null or not. But the problem is, whenever you don't find caudate is related to severity of motor symptoms, you don't publish it. And whenever you find it, you publish it and you say, see, as everyone else, we found that caudate is related. And then basically your meta-analysis can only help you as much as your literature. There are analyses to show you that all the p-values are around 0.05, but based on the current literature, the problem is that has been the norm. It doesn't necessarily mean that people were trying to make their p-values at 0.05. It can mean that, but it also can mean that when you don't have an effect, you just say it's not significant. And then the machine reads the paper, it just doesn't include it in the meta-analysis. That was the last one. Oh, and the sources of error can be random or systematic. If your source of error is random, that means you can average it out. You study multiple populations, you can look more and more. But if all your populations are white European, that source of variability is not captured, no matter how much you go and try to model that part of the equation. To give you some resources, I think the slides will be shared. These are really nice books and courses that you can go over, and they explain it much better than I do, but they have a lot more time as well. So then we go to a statistical learning, and we can basically reframe most of our questions in terms of a statistical learning. So the question of is group A different from group B comes that if I don't know which group the subjects belongs to or the data point belongs to, can I say with accuracy where it came from? And the accuracy is the threshold. So before we were talking about effect size and the p-values, now we are talking about how accurate I am. If you're looking at a population that 90% of people are having the disease, if your accuracy is at 90%, basically it means that you said everyone has the disease. It doesn't mean that you are 90% accurate. You are at the level of your population. And you need to define how random works and then say how much you are better than random. The question of association becomes the question of, again, predicting, but this time a continuous variable. And the question of treatment becomes that can we predict the effect of treatment? It can be changing the group assignment, or it can be changing the value of your Y. And machine learning traditionally is divided to supervised and semi-supervised and unsupervised learning. Supervised learning means you have your labels, at least for a good number of data points, and then you can make a model that can learn how your features or variables that you have measured are related to these data points and labels, and you can reproduce those labels or measurements. Unsupervised learning is you don't have any label. So you're trying to say, if I look at the distributions and I model the distributions, can I consistently group these data points together? And is there something interesting about this grouping? For example, what we do a lot is dimension reduction. So if you are doing an experiment and you are measuring 1 million voxels, you don't want to do 1 million tests. You want to look which variables are varying together and then make them one group. And you do one test. Are these variables, are these voxels related to any given intervention that I'm looking at? The semi-supervised, just to mention it, is that you have a few labeled data points, but you have a lot of non-labeled. For example, you do a task, you do a bunch of stuff, and then you win money. You did a lot of work and you got a raise this year. You did a lot of work next year, you didn't get. And then you're trying to do, what did I do right? What did I do wrong? You have not a lot of data points. You just get feedback at the end, for example. And this is what you do with animal experiments a lot of times. They do a lot of things during the trial, but then they get a reward or they don't get a reward. And we need to have a design that actually targets all the rest of the stuff can be averaged out, and that one feedback can be meaningful. So, supervised models. The first one is classification. We are saying, can we predict which group each data point belongs to? And a very nice application is the segmentation of tissues, lesions, or anatomical structures. Because if you're looking at healthy subjects, you're not necessarily even interested in the inference that the intensity of these tissues are different. What you want is to be able to segment these tissues in unseen data. You want to do automatically, you want to have automated quality control. You have 5,000 subjects that you did quality control, but now you have 50,000 subjects, and you might want to try to not repeat the process and try to make it automated. You might also do an inference, what was different between them, but that's not what you're really interested. You're interested to get new data sets and then not spend hours and hours of work for that. There's also another application where you classify your subjects, but then you're interested on the X and what is the factor that can distinguish these groups. Here are two examples. One is a famous data set that has basically helped the literature to go forward. And the question is basically, if you see a new handwritten number, what is the number? And you try to find features. You try to extract these numbers, make them to numerical 0 and 1s or gray density of the voxels, and then you try to predict what they are. The other one comes from Mallar's lab, and it's trying to do exactly what we talked in the previous slide, to segment subcortical regions. And then it can be applied into new subjects, and we can try to infer what is difference between subjects, different groups, and is it related to different measures. But the first step is accurately saying if this voxel belongs to caudate or putamen or not. And there are a lot of methods. I'm not going over them particularly, but it's good to know the names. So there are nearest neighbors, which basically you look at the data points on the X side and say, what is the closest data point? Who has the closest age, education level, is also a male because I have this person. And if that person had the value belong to group A, this other person also belongs to group A. And you can look at the K nearest people. Logistic regression is basically you have a linear regression, but you try to put it in a sigmoidal function and make a probability, calculate a probability if this data point belongs to one group or the other. The generative models is similar to the inference. You are trying to find the joint distribution between your X and Y, but then you try to make a line that separates the two groups. Support vector machines, they are trying to make a hyperplane. Think of it, if you are in a 2D space, there is a line, or if you are in a 3D space, there is a plane that divides your data points. This can be linear or non-linear, so the shape of the plane or the line can differ. And then the other groups, so in all of these, we are having parameters that we are trying to optimize to make our classifications more accurate. The neural network groups, the difference there is that we are also trying to learn the parameters without putting the features and engineering the features ourselves, without saying that, okay, I need to go and calculate the volume of different tissues and then remove the ones that are subcortical and only look at cortex. You try to give the model enough data that can basically the model is doing the feature engineering for you if you have enough data points. So here we have two groups that are highly separable. There's some overlap between them, at least in the two-dimensional space that we are looking. And based on the Bayes theorem, there is an optimal separation line. And we are using the K nearest neighbor model to basically say which data point belongs to which group. And what you are seeing here is your training data. So that is important because what you want to later on say your prediction comes from the data that is not presented here. So you look at the nearest neighbor or 10 nearest neighbor or 100 nearest neighbor. And then as you make your model more flexible, which here comes from one data point, basically with one data point, you can almost say who is coming from which group. So you have a really low error in terms of your training. But what is important is the green line here, which is your test error. So if you have an independent data set, how much error my model makes and how much based on the model that I have, based on the feature space that I have, how much flexibility can I produce in my model to predict the test data accurately. and it's in this particular case, you can see around 10 neighbors, has a line that aligns with the Bayes optimal decision maker pretty nicely. As your data points go up, the K value will go up, and you can do it better and better, unless your features are correlated, which we might talk about it later. So what is happening there? Yes.
So you go back 2 slides. I mean, this is an impressive group of methods. So just open up some discussion. How would you make a choice? How would you make a choice as to when you would choose a method, or when you know, it's kind of clear when you choose prediction or classification versus inference, but when would you choose? How would you decide to choose one of these methods?
The real answer is I don't have the answer. But from an application, for example, let's say we want to do segmentation. So here we know that the location-based measures or intensity-based measures are important if we are not going with neural networks that can decide for whatever it's deciding. Then we can say which one of these methods can have a prior distribution. So for example, Bayes becomes a natural way to go because we have a prior distribution, we have a prior map that can inform. If we are looking at neck level and we are saying we are in motor cortex, then that's easily not gonna be the case, and the Bayes by default doesn't let us do that. Whereas we might have a lot of thresholds to impose if we want to do that with random forest, if we want to go for multiple different anatomical regions. But then again, if there is an intensity, really sharp intensity difference across multiple features, a decision tree might be, a simple decision tree might be enough. And then you can say, okay, if it's bigger than this intensity in modality 1, but also bigger in modality 2, but not modality 3, I think that will work. There is, yes.
I can add it also really depends on the data you have and how much data you have and what the problem is. We don't know what the actual, like we are trying to replicate a function that we don't know what it is. If it's actually something super linear and super clean, then the more sophisticated the model is, the more noise you're trying to fix, right? So what ends up happening is that the most, like the simplest one is linear discriminant analysis or naive-based would work a lot better just because they don't really have enough parameters for you to fit noise. But then if you don't, especially when you don't have a lot of data, what ends up happening is that the more features you have, the more complex you make your classifier, the more you start fitting to that noise, and basically more complex models are not prone to error. But the other thing is that how much data do you have? If you don't have a lot of data, again, simple models, chances are similar models would be better because again, you would have a pure number of parameters to fit and estimate. So you're going to have a more robust, maybe a bit worse for the current data set that you're having, but it's going to be more robust in general. It's going to be more robust other data as opposed to the if you're not using it and a very limited amount of data, it's going to be very good for the local data that you have, but then you're going to data from another scanner model, another application tools, and you get like absolutely disastrous.
So just to repeat for Zoom people, the two other things that we are talking here is linearity, for example, versus non-linearity of the task that we are trying to make our prediction or classification. And if you're going for a task that is by nature linear and simple, using a non-linear method might overfit the noise because by nature it's looking at the non-linearities. If you have a lot of data points, you can still manage with even complicated models. But if you have a limited amount of data, you want your method match the complexity of your task. Even if your task is very complicated, if you don't have enough data points, complicated models won't work because you cannot estimate the parameters of the model reliably. And even then, simple models might work better. However, if you have a complex task and a lot of data points, then you want to use more complex models that can capture nonlinearities and other complex dynamics in your data. So, which brings us to overfitting. And what overfitting means is exactly that. If you have data points, you have 10 data points, and you have 10 parameters, basically you can memorize your trained data. And that is somewhat what is happening here. So you have complete prediction of your training data set. But if you memorize something, it doesn't mean if you have a new data set, that is how things work. And then you get a high test error. So overfitting is basically capturing random errors, noise, or individual variability that is not meaningful or related to your output variable that has been modeled within your predictive model. And it's going after them too closely. So when you have a new model data point that didn't come from that environment, didn't have that individual variability, then it will fail. And it relates to the issue of replicability and generalizability. So you want to obtain consistent results across the studies. And we will talk about this. So you want your data that you are training your model with to be data that is representative. And to do that, the way we go usually is we divide our data, or we basically superficially divide our data. In the division, we do training versus test, and that is when we can actually see if our model has overfitted. And within the training, because we need to optimize parameters, we also make a training data again and a validation data. And what you do is you train your model based on a given parameter, and then you see the performance of your model, and then you optimize your parameters. And when you are settled on a data based on your training data, then you apply it on your test data, and that will give you the expected error in the general population. If you don't have a lot of data, you can also do cross-validation. What that means is you divide your data in 10 groups, and then you train your model on 9 of them. You test it on the 10th, you optimize whatever you want to optimize, and then you apply it on your independent test data. But what you need in both cases is that the training data or the fold that you're using should be similar in terms of the group membership. You don't want 3 subjects from group A, 90 subjects from group B in your one fold, and you don't want your feature distributions to be uneven in your folds. So you don't want older people in one fold, younger people in another fold, and a lot of variability when you're going for your model. Yes.
Sorry about it. So you were just saying about similar group membership. So
based on your features.
yeah, sure. But what about in the cases where, say, you talked about ADME earlier, where your data set is actually representative probably of the true population?
Yeah.
Is it ever done, or is it a sensible thing to do to manipulate your folds so that your group memberships are something more representative of the true population distributions, rather than, because you might have that extra information available to you, just you don't have it in the data set naturally.
So the point is not that you can't do that. The point is when you are testing it, don't test it on ADME. Your test and training should be all representative. So if your representation is, I want people with 15 years of education, or I want people with cerebrovascular problems, you cannot train it and put those particular subjects in your training data set, do your folds properly balanced with them, and then look at the performance somewhere else. you need also a balanced group that you look at. As long as you can have a subset, if you look at UK biobank, if you have 50,000 subjects, then you can say, I just want to look at 40 years olds.
So I'm asking less about the specifics of that part of the distribution, but rather, you're undersampled for the existence of a certain group.
I'm saying you can match it as long as you have access to test the performance somewhere. So if you're only having access to ADME, even if you match your training model, you don't know the exact performance because you don't have an independent test model. And
well, it's kind of an implied
yeah,
generalizability.
but you definitely can do that sampling within the data set, which is not that much difference from sampling from the population. It's just we have a limited access to the population now, and we are sampling that. And we also do, it's also similar to the bootstrapping or permutation test that we do, that we sample within the population that we are doing.
I think that's a great idea, like, if possible, like, sometimes it's not possible. For example, in ADME, you have like 10% of ADME that has education that is like lower than college or university. So if you want to actually be representative of the population, you end up with a very small data set. So if you actually, like, there's always a trade-off between how much data you end up with and how representative the data is. But in general, it's also another thing that would be a good idea to try to balance, if possible, is, for example, if you're looking at the difference between sexes. But again, in ANDI, what ends up happening is that the proportion of AD versus MCI versus normal controls is very different between men and women. If you have like 40% of the males are AD versus 20% of the females are AD, the models that you would build, if you don't account for that, it would actually be biased towards healthier females.
Exactly, that's the kind of thing I'm asking.
So that is something that I would suggest you should try to actually balance within your training and validation.
Of course, you need to have access to the ground truths of the population level epidemiology studies.
And then a little bit more about epidemiological.
Yeah, no, for sure. But I think it's, in general, I think if you can do the train and test, you should go for it, because then it actually, you have two models that you can compare in a sense, and you can try to not do it and do it at the same time and see how much your prediction is changed. And you can kind of show that what is the bias there. So after we do classification, I'm going a bit over time, but we need to calculate the performance. And before we talked about type 1 error, type 2 error, statistical power. So here we talk about accuracy. Am I putting people who have Alzheimer in Alzheimer group and people who don't have Alzheimer in non-Alzheimer group? But also you have sensitivity and specificity. And what that means is you want to find positive cases when they are positive. You don't want a model that says everyone has Alzheimer, and then you basically get all the cases. And also you want a specificity. So you want to find that the cases are negative when they are actually negative. And what you're trying to optimize is sensitivity and specificity at the same time, while they're going in the opposite direction, and find the optimal point for that. This is a really nice table that relates what we are seeing in the machine learning to what we see in the statistical modeling. So one slide for multiple linear regression, because we do it a lot. And it just is, and it is one of the most common used methods in both inference and prediction. And the way it works is you're basically saying a linear combination of my features can explain my output based on a cost function. And this cost function can be defined in many ways. There also can be another term in the cost function that puts your parameters or your coefficients, so you can make them bigger or smaller depending on how you want to approach it. But basically what you are trying to do in inference is to make a regression model and then say, look at your beta values and see how much your X is contributing to your Y. And there are a lot of issues there that you need to be careful about. This slide is just here with 3 references, so you can go and look. For example, one is that the contribution of, let's say, X1 age to your parameter, which is volume of a region, is also related to your degree of education. Older people might have more education. And it's not just based on a conceptual level. If you calculate beta values, and if you look at the formula, the covariance of Xi and Xj appears in it. And also the covariance of different X features and the output appears there. So in one case, if you don't have orthogonal features and your features are correlated, what you are seeing basically reflects which feature you're measuring better. If you have noise in your education, but you know the age exactly, then the variance will be explained by the education. By whichever is more, I don't remember which one I said, whichever is more accurate, that is the one that will become significant. However, they are correlated, and it doesn't mean that is actually the contributing factor. Also, you might have proxy features that might be actual contributors, but you are looking at other factors and make them non-significant. So it has been said that it's straightforward, but especially when you use multiple linear regression, you need to look at the correlations between different features. You need to make sure how they relate to Y, and you need to do experiments. If you remove one feature, the model completely changes. So that means that while you are getting significant values, your model is not as stable. And then after that, you can try to start your inference. This was supposed to be. But the other thing you can do is you can say, can we predict Y from X? And that can be subjects age from MRI or cognitive scoring 5 years based on the MRI that you have. And what you are trying to do basically is to fit a line, which is a linear combination of your features. And your features here are basically different polynomial values of your x-axis. And what you are looking here is, if your model has nonlinearity, you need to have features that capture those nonlinearities and put them as features themselves. So the combination of linear features can capture them. So the nonlinearity is not in the model, but you can put it in the model as your feature space. And as you make your feature space more complicated, eventually you will overfit your data if you include more and more levels of complexity. So this is the last topic, dimensionality reduction. So here we are seeing 2-dimensionality reduction. And in one of them, we are trying to capture, here, let's say we are interested in the movement or in the direction of the movement of people. While we live in a 3D world, a 2D world can basically capture a lot of the variability in which direction we are moving. Whereas if we remove the information from one of the axes, we lost information. So the goal of dimensionality reduction is to reduce the dimension without loss of information. That is not achievable necessarily, but that is what we aspire to. And the methods that are widely used in neuroscience are PCA, ICA, and non-negative matrix factorization. So they have each different pros and cons. For example, PCA is deterministic, and it conserves the variance. If you basically use all your principal components in your new models, and then based on how much variance you want to explain, you can choose the number of PC components. But PCA doesn't ensure that your features are statistically independent if your data distribution is not normal, for example. ICA tries to make your features maximally statistically independent. So if you have different source of atrophy, if you have different source of degeneration in certain regions of your brain, ICA can help you to separate those statistically independent sources. That said, if your sources are also dependent statistically, then ICA cannot work there. Non-negative matrix factorization, similar to ICA, it's an optimization method. It's not deterministic, but what it has is a sparsity. And because it's non-negative and sparse, usually your coefficients can tell you the contribution of a factor to your output, and you can more reliably independently look at those factors because the non-negative aspects and the sparsity come together. Thank you. Yeah, Hasty books are both, the PDF is available, even the 2021 edition, and Cosmo Shalizi, like his lecture notes and his book is not published even.
Okay.
He has been saying that since 2013 that I started, I emailed him and he said, like, I'm planning to publish it with Cambridge. It's not published yet, but it's available and it's an amazing book.
Thanks. Any questions?
Everything so clear.
Any questions?
Yes.
Thank you so much for a wonderful presentation. I just was wondering in order to share this, if I fail to this room at a certain table, your alpha, can I change my alpha to
So the question is, why are you going to do that? That is the main reason, because what you define your threshold was based on a logic, right? Now you have done a study and you didn't find the effect and the null is not rejected. And then you can say, okay, what if I want to do an exploratory analysis, but not as a study, to look in the future collect more data? Can I now look if there is a trend in my data that later on I can try to get a better questionnaire there, measure those things better, and try to see if actually this trend is real or it's as the null hypothesis in this study suggested, just not there. And there might be things that the variance in your current sample is large, your measurement error is large enough and you don't have good measures. For example, you're looking at the CSF and certain markers are not as good, then you can try to say, is there anything there? But not for this study. It's always, if you do that, it's for future studies. Yes.
About the sampling bias, it's like torture for us in neuroimaging when you discover the bias of the data. And actually, my question is, how can you insert in the literature is unbiased? Just an example, like in my PhD, they for difficulty cognition after chemotherapy, they used to deny all patients who has some depression symptom.
Okay.
Once depression is the most common symptom after cancer treatments. And then we found that depression has a huge effect on the imaging results. So there is like a statistical fancy or way to make the authors say, okay, I want your paper.
No, it's I'm thinking that how much can a statistic do if you don't have the data? This is the problem. If you don't have the data, there's only so much your model can do. But which is good. I will say something after this. But if you have some data, then again, you can go and try to see how consistent within your data things are and try then to make a case to collect more data. But generally speaking, sampling bias can only be solved with more sampling, unbiased sampling. One thing that it's reminded and I wanted to say, but I didn't, is if you put new variables in your linear regression and your already existing variables become significant, be very cautious. Don't move forward and be just thinking that, okay, now we are controlling for this covariate and my variable is now significant. There are a lot of things that can be happening. And this is something that I'm not saying necessarily is wrong. Like this is a common practice. You can put your genetic variability with the first 15 principal components and see if your gene of interest is related. And while your gene of interest wasn't related to measure A, now that you put those PC variables, it becomes all of a sudden significant. So you need to see what is happening. It can be, for example, that one of your principal components is highly correlated with your gene of interest, and then it has a negative significant value, and your gene of interest has a positive significant value counteracting that, and together they're not explaining much of an effect size. So this is just something that is good to know. I learned it later.
So regarding your question about how do you deal with this kind of bias in the literature? So there are meta-analytic techniques for looking at whether or not the existing literature is biased. So if you can go and do a analysis of the entire existing literature, and there's something called like a funnel plot, where you can actually see whether or not the published studies end up centering around what is probably a true effect, or if there's a bias where you only see studies on one side. If you only see studies on one side of a funnel plot, what you can say is there's probably a file drawer effect, where where the studies that didn't have significance either were not published or were never done in the first place. And so that was actually the origin of a lot of the replicability crisis in psychology, because people started doing meta-analytic techniques and looking at these funnel plots and seeing actually all these studies are all biased because they never published the ones that didn't find it. There's just a hole where all these no effect studies should have been.
And for the effect that you are talking, it's difficult. But if you're measuring something that is measured generally, you can also try and go look at the clinical trials. They have better documentation, and failed clinical trials have the data. So when you're doing meta-analysis, a lot of times you don't see it in the literature or you see the bias, but then they go and look at the clinical trials, and if the variables are there, then you can see the effect is not there or is there.
It was actually registered ahead of time, right? So
yeah. So
Yes.
yeah. So that is the good thing about that. But they don't usually do neuroimaging. So
Yeah.
sometimes.
Yeah. It's just for the people on Zoom. We're going to end now. Thank you, Yashar, for a wonderful talk. And is there a lunch? Yeah. So for those of you who sign up for pizza lunch with Yashar, that'll be happening
In the conference.
in the CIC conference. Thanks a lot, everyone.